Now that we have some familiarity with what polar coordinates are and how to construct graphs using polar coordinates, we can start to look at some calculus concepts using polar coordinates. The first one we'll take a look at is how we might calculate the slope of a tangent line for a graph given in polar coordinates. The thing to keep in mind when you contemplate the slope of a curve given with polar coordinates is that even though the points on that curve are defined by their radii and their angles, the slopes at those points are still going to be defined in terms of x and y, or horizontal and vertical components. In other words, even though the curve is of the form r equals f of theta, the slope is still of the form dy over dx. This doesn't mean, however, that we need to rewrite our equation in Cartesian form. Instead, we can use the familiar relationships between r, theta, y, and x in order to come up with a new formula that'll help us calculate the slope. Let's take a walk through how we might come up with such a formula. If we start off with a polar curve in the form r equals f of theta, then we can recall that we know that x is equal to r cosine theta and y is equal to r sine theta for any point living on that graph. Replacing r with f of theta, we then know that x is equal to f of theta times the cosine of theta, and y is equal to f of theta times the sine of theta. Now we apply the product rule. This gives us that dx d theta is equal to f prime of theta times the cosine of theta minus f of theta times the sine of theta. Similarly, another application of the product rule will tell us that dy d theta is f prime of theta times the sine of theta plus f of theta times the cosine of theta. Now we know that dy dx is the same thing as dy d theta over dx d theta using the chain rule. Putting all of these pieces together, we come up with a formula for dy dx. dy dx is then equal to f prime of theta times the sine of theta plus f of theta times the cosine of theta, all divided by f prime of theta cosine theta minus f of theta sine theta. Let's see if we can use this formula to find the slope of the tangent line in the image that we started off this video with. So that curve is actually the curve r equals 2 minus 2 sine theta. And that line is occurring for a theta of value of negative pi over 4. So our f of theta is going to be 2 minus 2 sine of theta. And f prime of theta, taking the derivative of that with respect to theta, is going to be negative 2 times the cosine of theta. Now notice that is not the slope of the tangent line. That is a relationship between r and theta. The slope of our tangent line is a relationship between x and y. It's horizontal and vertical components determine the slope of that tangent line, not radii and angles. If we look at theta, the cosine of negative pi over 4 is going to be equal to the square root of 2 over 2, and the sine of pi over 4 is going to be the negative square root of 2 over 2, and we'll use those components repeatedly as we construct our formula. So notice that f of negative pi over 4 is then 2 minus 2 times the sine of pi over 4, which is negative root 2 over 2, and when we multiply that out, we get 2 plus the square root of 2. F prime of negative pi over 4 is negative 2 times the cosine of pi over 4, or cosine of negative pi over 4, which is root 2 over 2. So here we get negative square root of 2 as f prime of negative pi over 4. So now we're ready to put this into our formula. So we get that dy dx is equal to f prime of theta, so that is negative root 2, times the sine of theta, which is negative root 2 over 2, plus f of theta, 2 plus root 2, times the cosine of theta, root 2 over 2. That's our numerator. In our denominator, we get f prime of theta, negative root 2, times the cosine of theta, root 2 over 2, minus f of theta, 2 plus the square root of 2, times the sine of theta, negative root 2 over 2. We'll tidy that up. So negative root 2 times negative root 2 over 2 gives us positive 1. Distributing, we're going to get root 2 and another positive 1. In the bottom, negative root 2 times root 2 over 2 gives us negative 1. The two negatives that we see there end up making the remaining terms all positive, so we're going to get a positive root 2, and then we're going to get a positive 1. So adding things up, we get 2 plus root 2, all divided by root 2, and when we divide both of the terms in the top by root 2, we end up with the square root of 2 plus 1 as the slope of the tangent line to that cardioid that we see in the image. All right, let's look at one more example. This time we're going to look specifically for vertical and horizontal tangent lines. So we have the curve r equals 2 sine theta. And we know that that is a circle. That's a circle with a radius of 1. Its center is at the point 0, 1. So the y-axis is running down through the middle of it. So you should have, if you can picture that in your mind, you should have some sense of where the tangent lines are that are vertical and horizontal are for this. Notice that theta just is going to be between 0 and pi. If theta gets bigger than pi, we start making laps around the circle, and we don't need to do that. So we're just going to isolate our answers to values of theta that fall between 0 and pi. All right, so if r is 2 sine theta, that means we're working with an f of theta of 2 sine theta, which means that f prime of theta is 2 times the cosine of theta. So we can use that to start piecing together our derivative. We know that dy dx is going to be equal to f prime of theta, that's 2 cosine theta, times the sine of theta, plus f of theta, 2 sine theta, times the cosine of theta. And then the denominator, we get f prime of theta, that's 2 cosine theta, times cosine of theta, minus f of theta, 2 sine theta, times the sine of theta. So if we clean that up, we get 4 times the sine of theta cosine theta over 2 cosine squared theta minus 2 sine squared theta. Okay, and so now we know that this is going to be 0 where the top is 0 and the bottom isn't, and it's going to be undefined where the bottom is 0 and the top isn't. So let's look at those separately. Let's look at where 4 sine theta cosine theta equals 0. So this is where our numerator is 0. That happens when either sine of theta is 0 or the cosine of theta is 0. Well, between 0 and 2 pi, that happens at theta equals 0, theta equals pi, that's where the sine of theta is 0, and where theta equals pi over 2, that's where the cosine of theta is 0. We also have 2 cosine squared of theta minus 2 sine squared of theta is 0 for our denominator. Well, that's going to happen where 2 cosine squared of theta equals 2 sine squared of theta, or where the cosine squared of theta equals the sine squared of theta. And if we take square roots of both sides, that means that the cosine of theta is going to be either the positive or negative sine of theta. And between 0 and pi, that happens when theta is either pi over 4 or 3 pi over 4. So since there's no overlap between those two groups of answers, that means that these answers give us the horizontal tangent lines. And these give us the vertical tangent lines. So we started off with r equals 2 sine theta. Well, for theta equals 0, pi, and pi over 2, when theta is 0, we get r is 2 times the sine of 0, so that makes r 0. So we can see that in polar coordinates, one of our horizontal tangent lines is occurring at the polar point 0, 0. And when theta equals pi over 2, we get 2 times the sine of pi over 2, which is 2. So we have it in polar coordinates again, we have 2 pi over 2 as the place where the second horizontal tangent is occurring. But those are in polar coordinates. Let's do the same thing for the vertical tangent lines. When theta is pi over 4, r is going to be 2 times the sine of pi over 4, which is going to be, the sine of pi over 4 is root 2 over 2, so we get square root of 2. And when theta is 3 pi over 4, we get 2 times the sine of 3 pi over 4, which is also root 2. So we have the points, again in polar coordinates. These were our horizontal tangents. And at the points root 2 pi over 4 and root 2 3 pi over 4, we get our vertical tangents. Now, let's think about those with regard to Cartesian coordinates. We know that x is going to be our cosine theta and y is going to be our sine theta. So at the point 0, 0, in polar coordinates, so these are our polar over here, our Cartesian is going to be the point 0 times the cosine of 0. Well, that's 0, and 0 times the sine of 0. So that one's still 0. The point 2 pi over 2 is going to translate to x will be 2 times the cosine of pi over 2, which is 0. And y is going to be 2 times the sine of pi over 2, which is 2. So these are our Cartesian coordinates over here. So we can see that we have tangent lines at the top and horizontal tangent lines at the top and bottom of our circle. And then if we look at root 2 pi over 4 in polar, that's going to translate to root 2 times the cosine of pi over 4, which is root 2 over 2. So that's 1. And then root 2 times the sine of pi over 4, which is also root 2. So we get 1 there. And then root 2 3 pi over 4. Translating that to Cartesian, we're doing root 2 times the cosine of 3 pi over 4, which is negative root 2 over 2. So now we get negative 1. And then root 2 times the sine of 3 pi over 4, which is positive 1. And this is going to be the right and left-hand sides of our circle in Cartesian coordinates. So our key takeaway here is that when we have a curve that is expressed in terms of polar coordinates, something of the form r equals f of theta, the slope of its tangent lines are still measured with respect to vertical and horizontal changes. So that in order to find the derivative, we still need to look at dy dx. But we can use relationships that we know between r, theta, x, and y in order to express that dy dx entirely in terms of theta. So we come up with this formula. It's a little bit complicated to look at, but once you use it a few times, it ends up being not terribly tricky. And we can use that to evaluate slopes for given values of theta, and we can also use it to find horizontal and vertical tangent lines for our curves.